This is question 30b of the 2015 CSSA paper for general mathematics. It says the scatter plot shows the relationship between the daily calorie intake and body mass index BMI for a group of 15 adults. The correlation coefficient for the data is 0.93. Explain what the correlation coefficient indicates about the relationship between daily calorie intake and BMI for these adults. Well, in this question here, all you need to understand is the significance of the correlation coefficient. Now, the value of R, or the correlation coefficient, in this case, indicates a strong positive relationship between daily calorie intake and BMI. Okay, and you can see just on the graph there that the data points are all very closely aligned, almost in a straight line. Obviously, if it was a perfectly straight line, you'd have a correlation coefficient of 1, which is the maximum you can have, which describes basically a perfect linear relationship between the two variables. So to answer this, you just write the value R indicates a strong, and you've got to use the word positive, relationship between daily calorie intake and BMI. Now, to answer this question, you've got to make sure you state what sort of correlation you have. In this case, because the number is 0.93 is close to 1, we have a strong positive relationship or correlation. If it wasn't close to 1, you wouldn't use the word strong, but because it's over 0.9, you'd say it's a strong positive relationship. If it was less than 0.9, you'd still say it's a positive relationship, okay, or moderate. Now, and you've also got to state what the variables are that you're comparing. So in this case, the daily calorie intake and BMI. It's not enough really just to say strong positive relationship. You've got to put it into the context of the question. Just one thing to note also, for some reason, some students, when it comes to correlation type questions, use the word skew. Now that is absolutely not relevant, has any connection between correlation. So if you are one of these people who use the word skew in this situation, get rid of it, because you're just going to get it wrong. Skew is to do with the distribution of data, nothing to do with nothing at all to do with correlation or relationships between two variables. So the only words to use here, relationship or correlation, and make sure you have strong positive relationship stated here. And obviously don't forget to mention what variables you're comparing. Okay. What I haven't mentioned at this point yet, which I should have earlier, is the fact that a strong positive relationship or a strong positive correlation basically means that as the daily calorie intake increases, so does the BMI. Okay, that's what a positive correlation is. As one variable increases, so does the other. And just for future reference, if you have a negative correlation, so basically the points, the datum points, will be aligned in the opposite direction. It means as one variable increases, the other decreases. So basically, in summation, what this all means in this scenario is that as the daily calorie intake increases, there is a strong relationship in the fact that so does the BMI increase. Okay, so that is what a strong positive correlation actually means. Okay, part 2 of question 30b The table below shows the mean and standard deviation for calorie intake and body mass index. By making use of the formula on the formula and data sheet, the information in the table and the value of R, which is the correlation coefficient, are given. Find the equation of the least squares line of best fit. Okay, so first thing you need to do is go to your formula sheet and find the method or the formula you need to use in order to find the equation of the line of least squares line of best fit. Okay, now once you've identified the formula, you'll know that y is equal to the gradient times x plus the y-intercept. Okay, in this scenario, when we're dealing with the least squares line of best fit, the gradient isn't the gradient as in terms of how you think of it traditionally, where it's just rise over run. The gradient in this case is influenced by the correlation coefficient and acts almost like a type of a scale factor to accommodate the fact that the points aren't aligned in a straight line. So the correlation coefficient, I guess, is an adjustment to the gradient to accommodate the fact that the lines aren't aligned in a straight line. So as indicated on your formula sheet, the gradient is actually found by, so I'll just use M to represent gradient, by multiplying the correlation coefficient with the standard deviation of your y-scores divided by the standard deviation of your x-scores. Now, that's already given to you, and it's nicely indicated. X-scores, that's your standard deviation for x, standard deviation for y. So to find out the gradient, you just plug it in. So 0.93 multiplied by the standard deviation of y is 3.08 over standard deviation of x, which is 357.77. Now, when you multiply, plug it into your calculator, you get a gradient. It's quite long-winded, approximate gradient of 0.008. Okay, now the y-intercept, once again, when we're dealing with least squares line of best fit, isn't a simple case of where the line cuts the y-axis, and it's found by looking at the mean of y scores minus the gradient, which you just worked out, multiplied by the mean of x scores. Now, this is, once again, we're not going to go into why, but it accommodates the fact that the line, so the points aren't aligned in one straight line. So someone smarter than me and smarter than you have worked out that this is the way to accommodate the variations in, I guess, where the y-intercepts could be, to accommodate for the alignments of the points. Okay, so, but for what all you need to do is make sure you know where to find this on the formula sheet and plug in the right values accordingly. So the mean of y is 23.84 minus, now the average you've worked out already over here. Just use the value on your screen, multiplied by the mean of x, which is 2,200. Oops, 2,200. Okay. Once you plug that all in, you get a value of 6.23. Okay. So therefore, you can say, let's make some space here, the equation of the line, or the least squares line of best fit, has an equation of y equals 0.008 8x plus 6.23. Okay, and that's it. That's how you find the least squares line of best fit. Like I said to you, just make sure you're aware of the different variables required that are indicated on your formula sheet to find the least squares line of best fit. Okay, so question 30b part 3, explain why the equation of the least squares line would not be reliable for predicting the BMI of a person who consumes 5,000 calories daily. Now, if you refer back to your graph, as you can see, I mean, it only goes up to 2,800. So the fact that you're nearly doubling the daily calorie intake in your equation, it's too much of an extrapolation. It's too far removed from the data that you've collected. So the answer here, what I would write, would be 5,000 calories is too far removed. From the calorie intake data that was used or collected to establish the least squares equation line of best fit. Okay, so basically what you need to indicate here is that you recognise the fact that the data used is limited, and so therefore the equation that you've established earlier is based on the data that goes from only up to 2,800. So it's going to be a very big assumption to assume that the trend will continue up to 5,000 calories. So because it's so far removed, I mean, if you could argue you could go up to 3,000 calories and use the equation, but 5,000, it's too far removed. You can't make the assumption that the correlation or the relationship will continue in the same vein for that far. So therefore, this least squares line of best fit, the equation of this least squares line of best fit would not be appropriate to predict a BMI of a person who consumes 5,000 calories daily. Hope that makes sense.